Did you know that the device you are using right now contains billions of invisible switches, each one smaller than a virus? These are called transistors, and they are the fundamental building blocks of every digital device on the planet. For over 5 decades, engineers kept shrinking these transistors to make computers faster, more efficient, and more powerful, a relentless march of progress that became known as Moore's Law. Today's most advanced chips pack over 100 billion transistors into a space no larger than your fingernail, named after Intel co-founder Gordon Moore, who first observed the pattern in 1965. This law predicted that the number of transistors on a chip would double approximately every 2 years. For decades, that prediction held true, fueling a technological revolution that gave us smartphones, artificial intelligence, and the modern internet. But around 2015, something alarming happened. The pace of progress began to collapse, and the entire technology industry found itself staring into a very uncertain future. How chips are born: light, silicon, and precision. To understand why Moore's Law hit a wall, we first need to understand how microchips are actually made. It all begins with silicon dioxide, essentially purified sand, which is melted down and grown into a large single crystal ingot. This ingot is then sliced into thin wafers using diamond wire saws, polished to a mirror-like finish, and coated with a light-sensitive material called photoresist. A single silicon wafer can eventually yield hundreds of individual chips. Light is then shown through a patent mask onto the wafer, exposing certain areas of the photoresist. A chemical wash removes the exposed material, leaving behind a precise pattern. The exposed silicon is etched away or filled with metal conductors, creating one layer of the chip. This cycle: coat, expose, etch, deposit, can repeat anywhere from 10 to over 100 times, stacking layers of transistors and wiring into an impossibly complex nanoscopic city. The light problem: when physics becomes the enemy, the key to making smaller chips lies entirely in the wavelength of light used during the exposure step, a process called photo. The shorter the wavelength, the finer the features you can print. For years, the industry used deep ultraviolet light at 193 nanometers. With clever engineering tricks like multi-patterning, chip makers squeezed every last drop of performance from this approach. But by 2015, they had reached an absolute physical limit. No amount of engineering cleverness could push further. The problem is rooted in a phenomenon called diffraction, when light bends and interferes with itself as it passes through tiny gaps in the mask. As features shrink toward the wavelength of the light, diffraction causes patterns to blur and overlap. To print even smaller features, you either need a larger lens system which has a hard physical ceiling, or you need a fundamentally shorter wavelength of light. And that is where one of the most audacious ideas in the history of engineering was born. A crazy idea from the 1980s: X-rays for chips. In the early 1980s, a Japanese scientist named Hiroki Kinoshita proposed using extremely short wavelength light, around 10 to 13 nanometers, to print chip features far smaller than anything achievable with conventional methods. This region of the electromagnetic spectrum, known as extreme ultraviolet or EUV, lies between traditional ultraviolet light and X-rays. The theoretical benefits were enormous, but almost immediately, the physics fought back with a vengeance. At these wavelengths, even air absorbs the light completely, meaning the entire system would need to operate in a near-perfect vacuum. Worse, traditional glass lenses are also opaque to EUV radiation, making conventional focusing systems completely useless. When Kinoshita presented his early results at a major scientific conference in 1986, the audience was openly skeptical. His findings were dismissed as a big fish story, and the scientific community largely turned its back on him. Yet he refused to give up. The mirror that could, a breakthrough from a nuclear lab. The solution to EUV's focusing problem came from an unexpected place: Lawrence Livermore National Laboratory, a facility originally built to study nuclear weapons. Scientists there, working on capturing X-ray light from fusion reactions, had developed a remarkable new type of mirror. By stacking alternating ultra-thin layers of different materials like silicon and molybdenum, each just a fraction of a nanometer thick, they could reflect EUV light through a process of constructive interference. The result was mirrors capable of reflecting up to 70% of EUV light at 13.5 nanometers, a genuine scientific breakthrough. Physicist Andrew Horlock, inspired by this technology, proposed applying it to chip lithography. He presented his idea at a conference in 1988 and was promptly laughed off the stage. Every expert in attendance lined up to explain why it could never work. Yet just days later, a phone call came from the executive vice president of AT&T's Bell Labs, who had heard about the work and wanted to learn more. Sometimes, all it takes is one believer to change the course of history. Building a sun on Earth, the source of the impossible light. By 2000, a consortium of U.S. national labs had built the first working EUV prototype, called the Engineering Test Stand. It could print features as small as 70 nanometers, proving the concept worked. But there was a devastating problem. It could only process around 10 wafers per hour. For commercial semiconductor manufacturing, you need hundreds of wafers per hour, running non-stop 24 hours a day, 365 days a year. That meant the light source needed to be at least 10 to 20 times more powerful, a seemingly impossible leap. The answer was laser-produced plasma. by firing an incredibly powerful laser at tiny droplets of molten tin, each one smaller than a red blood cell, and heating them to over 220,000 degrees Celsius, roughly 40 times hotter than the surface of the sun. Engineers could generate a burst of EUV light. The key innovation: instead of hitting each droplet once, hitting it with a pre-pulse first flattens it into a thin pancake shape, dramatically increasing the surface area and conversion efficiency of the final, vaporizing blast. ASML and the machine nobody believed was possible. One company refused to give up when others walked away. ASML, a Dutch firm based in the unassuming city of Eindhoven, Netherlands. Over 3 decades, ASML poured billions of dollars into turning EUV lithography from a laboratory curiosity into a commercial product. Their machine must fire 50,000 to 60,000 tin droplets per second, hitting each one with 3 precisely timed laser pulses, with 0 misses allowed. It houses mirrors so smooth that if one were scaled to the size of the Earth, its largest imperfection would be thinner than a playing card. The entire optical system must align chip layers to within just 1 nanometer, the width of 5 silicon atoms. Even as parts of the machine accelerate at over 20 times the force of gravity, more than 5,000 supplier companies contribute 100,000 individual components, 3,000 cables, 40,000 bolts, and 2 kilometers of hosing to each machine. Shipping a single high-NA EUV machine requires 25 trucks and 7 Boeing 747 cargo jets. Each machine costs over 350 million euros, and ASML remains the only company on Earth capable of building one. The unreasonable dream that changed our world. EUV lithography took more than 30 years, billions of dollars, and the combined effort of thousands of scientists and engineers across multiple countries to become reality. The first commercial EUV chips reached consumers in 2019, and nearly every high-end smartphone processor made today relies on this technology. ASML's machines now represent one of the most critical choke points in the global technology supply chain, making them perhaps the single most strategically important manufactured product in the modern world. What strikes us most about this story is not the engineering, astonishing as it is, but the extraordinary human persistence behind it. People like Kinoshita and Harilik were told, repeatedly and publicly, that they were wrong, that their ideas were impossible, and they kept going anyway. As George Bernard Shaw once wrote, all progress depends on the unreasonable person. We at the World Documentaries believe these are exactly the stories worth telling. If this video sparked your curiosity or gave you a new appreciation for the technology in your pocket, drop your thoughts in the comments. We genuinely want to know what amazed you the most. Like this video, subscribe to the World Documentaries, and join us next time as we uncover the next extraordinary chapter in human ingenuity.